Hi, welcome back. In this video, we are going to talk about an efficient sorting algorithm, which is called merge sort. We're going to look into how it works, but most importantly, we'll see how it is more efficient than bubble sort, which we discussed in the previous video. In this case, the merge sort, it has a time complexity of n times log n, which is linear arithmetic, right? And the bubble sort, you remember, it was n squared. And here is just an example of how they compare. As you can see, n log n is obviously not as efficient as n, right? But for some algorithms which require actually some sophistication, like sorting algorithms, where it's very hard or almost impossible to had ON average time complexity, n log n is pretty good actually, and much better than n squared, as you can see this difference here. All right, before we dive into merge sort is an example of divide and conquer algorithm. Divide and conquer is just an idea, or as you can see, it's a design paradigm that basically tells you that you can split a big complicated problem into smaller problems, which would be of the same type. You'll see what it means on the example of merge sort in a minute. So here, if I just read what it says here, we recursively break down a problem into smaller subproblems until these become simple enough to be solved directly. This is exactly what happens with merge sort, and so dividing is not the only thing that divide and conquer recommends. So here, first we divide, so we break problems into subproblems. Then we solve those simpler versions of the problems, and then we combine. So we combine the solutions of those subproblems to create a solution to the original problem. This is exactly what happens with the merge sort, and let's actually see how it works on this example. Now, the idea of the merge sort is actually to split the array into sorted sub-arrays, right? And the way you do this is actually interesting. So let's imagine we have this array here, right? So it has 5 elements, it's unsorted. And this is the first step, right? So we just got the array. Now the second step would be to split it into 2 sub-arrays, right? And at this point, of course, there will be unsorted, even though actually this part, you can see it's already sorted, but let's ignore that for now. So we split it into 2. On the next step, we actually split each one of those also into sub-arrays. So for example, here we split it into 7 and 5 sub-array and 1 sub-array. And this one is split to 2 and 9. Now you see those 1 element arrays here, 1, 2, and 9, those are separate arrays, right? And we can actually say that each of those arrays are sorted because they only have 1 element, right? So we kind of have already a solution for those sub-arrays. The only thing would be to use this information to actually solve the bigger problem. Now we continue and we split the 7 and 5 sub-array into 7 and 5, so 2 different sub-arrays. And at the end we have kind of 5 different sub-arrays, and each of those sub-arrays are sorted. Because they only have 1 element. Now, the idea from now on is to actually merge them back together. And here's how we do that. So first, we take 2 sub-arrays, right, and we try to merge them. So when they have only 1 element, it's pretty straightforward. So we just compare 5 and 7, and we say, okay, 5 is less than 7, so 5 should go to the left and 7 should go to the right? And we get 5 and 7 sub-arrays. So this sub-array is also sorted now. Then we have 1, 2, and 9. And now we compare 5 and 7. So this sub-array and this sub-array. So 5, 7, and 1. And we say, okay, first we take the leftmost elements here and here. Here we only have 1 element. Here it would be 5. And we compare them. And imagine there is like a new sub-array that we create. And we say, hey, which of those elements, leftmost elements, we should take to have a sorted subarray. And we say, okay, since 1 is less than 5, we take 1 first, then we only have 5 and 7. And then we say, okay, then we take 5, and then we take 7, right? And then we have 1, 5, 7 subarray, and 2 and 9. Now, on this step, we actually compare 1, 5, 7 and 2 subarrays, right? Or actually, no, actually we compare now those two because they were split in that order, and we have to combine them in that order as well. So here we started with 7 and 5 because originally it was one original subarray, right? Therefore, we merged 7 and 5 and then 7, 5 and 1 into one, right? And then we got a sorted subarray that has exactly those elements. Now we actually combine this one, and here it's once again pretty simple. If we compare leftmost element of this subarray and this subarray, it will be comparing 2 and 9, and 2 is less than 9, so 2 goes first to our new subarray, and then 9 goes there. And now we have two merged, two sorted subarrays, right? And now we do the same thing. So we create kind of a new array. Let's just imagine, so here or here, and we compare the leftmost elements. So here we take 1 because 1 is less than 2. We took 1, and then we compare 5 and 2. And we say, okay, 2 is actually less than 5. So now we take 2 from here. So we kind of have 1, then 2, and then we compare 5 and 9. We say, okay, 5 is less than 5 is less than 9, right? We take 5, and then we compare 7 and 9, and we take 7, and then we take 9. Here is actually the breakdown. So here we had, for example, so we started with 1, 5, 7, 2, 9, right? And or actually, no, we started here. Where did we start? I'm already a little bit mixed up. So yeah, here we started, right? And here is the process. So we take 1, then we take 2 from here, and then we take 5, 7, and 9. And now the whole area is sorted, right? It's pretty straightforward, actually, the way it works. But as you can imagine, for example, if you would be given 100 elements array, you would need an algorithm that would do all this stuff for you, because going through it manually would be troublesome. But the algorithm behind it is still the same. So here's the code for it. As you can see, it is split into 2 parts. We can look into it in the playground. So here is the first part of the algorithm, which is the splitting, right? So we say, hey, we take an array and we actually recursively split it, right, until we only have one element, as you can see. So this would be a recursion, this would be the base case of recursion, and this would be the other case. And for each time we call the function, we actually split it. So we take the first half of the array. So here we use the middle index, right? So the one in the middle. And then we say, okay, let's create a new array. And then let's create a new array from, let's say, from the middle to the right, and another one would be from the left to the middle, right? So now we have 2 subarrays. And since we do it recursively, then, for example, this subarray would be called with merge sort and will be split into another subarray another time until we get to this base case, and the recursion stops. Now, when the recursion stops, now we have kind of like on each step we have left and a right array here, and we go to this case here, right? And now we do the merging, all right? So since we have a left and right subarray, remember when we finish splitting, right? So we get all the elements separated, so as we see here, and now we kind of merge them back, right? And for merging, we actually use this function, right? So we have left array and right array. So we have left index and right index, and also the result for the combining array. Now in this while loop, you see we traverse the left and the right array, and we select the leftmost elements, all right? So for example, of the first array, we check if the leftmost element of the left array is less than the leftmost element of the right array, and we compare them. So it's the same thing as we did, for example, here, or let's make it more complicated. So, for example, let's talk about those two. So 5, 7, and 1. So we the first index of the left array would be pointed to 5, and for the right array pointed to 1, right? And then we compare them and combine them, right? And for more complicated example, as here, for example, we start with an index pointed to 1 and here to 2. We compare them. We say, okay, we need 1. Then the index increases here to 5. This is what happens here. So left index increases to plus 1, right? So to the next element, which now points to 5. And now we compare again, since it's a while loop, we come here again. The left index is now 1 more, right? And we compare them again. So now we compare 5 and 2. And this time 2 is less than 5. So we go to the else case. And so, yeah, we append the elements to the resulting array. And we do this until we have elements in each of the arrays. So you see the while loop runs until we run out of elements. So when we put all the elements into the new sub-array, we finish merging. And then we can also merge every sub-array this way recursively, but going backwards, let's say. So now we also have the example of how it runs, right? So we had the same array. Now let's say we run it, and as you can see, it sorts the array exactly as we want. All right, so here, this part actually is just for the case where we run out of elements in one array, and we still have a bunch of elements in another array. For example, I think we had this case when on the right we only have one element. So, for example, maybe here, for example, or maybe here, right? We only have one element here, 2, and then when we take 1, this array becomes empty, and then we just append this whole array to the resulting array. That's why we have those two lines here. All right, so this is the implementation and basically the idea behind it and how it works. There's just additional visualization if you want to see it. Now, if you analyze time and space complexity, it's slightly complicated, but we'll try to break it down and make it simple. So let's start with space complexity or time complexity. Let's see. Yeah. So with yes. So this is here probably. No, it's all talking about n log n. All right. Let's start with n log n. So the time complexity. As you can see, we have this logarithmic part here, right? And if you don't know what that is logarithm is a mathematical function. And so here is an example. So logarithm, here you see 2. 2 is a base. And 8 is like a parameter that you pass into it. And then it produces a number. So in this case, the result would be 3. Now, how 3 is produced, or why is it 3, right? Just in case you don't know. So this statement, so log with a base of 2 of 8 means it's like answering the question, to the power of which number should 2, which is the base, be put to get an 8, right? So if you take a 2 and take the result, which is 3, 2 to the power of 3 is equal 8, which is exactly the number that we started at. So it's kind of like the reverse of the power function, right? So just to prove the point, 2 times 2 times 2, so 2 to the power of 3, because you see we have 3 2's here, we get an n, or we get an 8 here, right? So this is what logarithm means here. And now why we decided that our time complexity is somehow related to log, right? So here's the thing. We said that we want to divide an array, right? And let's say we start with an element with an array of 8 elements, right? And we want to divide it. Now the question is how often or how much can you divide it until you get to 1 element, right? Since we split the array each time into 2, here's how many times we can split it. So we take an 8. Then we split it and we get a 4. Then we split it again, we get 2, and we split it again and we have 1. So how many times can we split an array of 8 elements into 2? It will be 3 times. Now with 16, for example, will be just 1 more. So it's not plus 8, but plus 1. Here's the reason. So we have 16, we split it, we get 8, then 4, then 2, then 1. So exactly as here as well. So the splitting process gives us the log n part, you see, because we split not, so the amount of splitting is not related directly, so linearly to the number of elements, but logarithmically, which gives us better results, because log n is actually always smaller than n. Here's the proof. So for example, if you take n of 8, so n equals 8, right? And for example, n and n equals 8 would be 8. If we take log n, which would be log 8, it will produce 3, and 3 is smaller than 8, right? So log n is better than just n. All right, so this would give us the log n part, right? So here it's more explanation of the log n. So the number of times we can split n in half is log base 2n. Here's the example, which we already covered. And the n part is actually the merging part, because each time, so here we can kind of build a tree of splitting. So here we split once, then split another one, and split again. And you can say that, hey, we splitting here 2 times, right? So we split this here and here. But since they are happening inside the same function here, we can say that it's like two operations, and 2 is a constant, so we just remove it. Now with merging on each level here, we just merge at maximum n elements, which would give us these space complexity. Actually, this is why the n complexity as n, because, for example, at each point, so this is first step, second step, third step, fourth step, we always use at most n, so an array of n elements or different arrays, but if you sum them all up, for example, on this level, if you sum them all up, it will be down to 5 elements, which is n, right? And the merging also takes at most 5, or in this case, so for example, here, if we would start merging on this level, which is not correct, we should start merging, for example, here, right? So we start merging, and we actually process n elements, because we compare this, and then, for example, then we would compare 2 and 9, right? And 1 and 7 and 5, right? So on each level, we would also process n elements. That's why in the time complexity, we not only have log n, but first we have n. So it's kind of like, it's almost n squared, but a little bit less than that, right? And if you look into it here, so in terms of the time complexity, looking at the code, so the log n part comes from the recursion, right? Because we do the recursive call log n times, once again here, right? We do it twice, but still. And the n part, so times n, we get from this part when we actually merge it, because here when we have left and right arrays, we traverse it from left to right, both of them, right? And in sum, it will, for the whole level, it will be be exactly n elements. All right. So the good part is actually that it will be very unlikely that you'll be asked to implement one of those sorting algorithms on the fly during the interview, but it's just important to understand how they work and how you could implement at least one efficient sorting algorithm that you can use every day with just using array.sort, which would produce the same efficiency. All right, so that's it. It's more like a theory and background into algorithms, sorting algorithms, and also maybe another example of log and type complexity, which can be complicated to understand. All right, so that's it for this video, and we see each other in the next one. Ciao, ciao.